questions 21 through 25 on the 2012 grade 12 AMC 12A. Let a, b, and c be positive integers with a greater than b greater than c such that this equation and this equation exist. What is a? Well, the first thing we need to do in this question is take this first equation and add it to that second equation. And when you do, you get 2a squared plus 2b squared plus 2c squared minus 2ab minus 2ac minus 2bc, and that is equal to 2011 minus 1997, which is just 14. Now at this point we do some very nice factoring, but first we have to group these. So I'm going to take the first a squared and group it with the minus 2ab plus 1b squared and put that in brackets. Then I'm going to take another a squared and group it with the minus 2ac and one of the c squareds, put that in brackets. And then I'm going to take one of the b squareds and group it with the minus 2bc and one of the c squareds and put that in brackets, and that's all equal to 14. And now this factors very nicely. A minus b squared plus a minus c squared plus b minus c squared, and that is equal to 14. So we have one perfect square, another perfect square, and another perfect square. 3 perfect squares that add up to 14. And the only way that is possible is if you have 1, 4, and 9, right? 1 is a perfect square, so is 4, and so is 9. And the sum of those 3 add up to 14. But the question is, which one is which? Do I put 1 here, 4 here, 9 here? How does it work? Well, one thing is for sure, that because of this inequality, that a is greater than or equal to b, which is greater than or equal to c, that a and c have the greatest difference. So a minus c must be the biggest of these. So this must be a 9. Now the other ones, 1 and 4, I am not 100% sure. So we will take a guess. We'll put 1 and 4 for each of these. So I'm going to put the 4 here and the 1 here. If I guessed wrong, I just do it again with the 1 here and the 4 there. Because the key is that in the end I have to come up with a integer value for a. So let's see what happens. If a minus b squared is equal to 4, that means a minus b is equal to 2. And very similarly, that means a minus c squared is equal to 9. So a minus c must be equal to 3. And b minus c is equal to 1. So with these, what I'm going to do is just isolate for b. Isolate everything in terms of a, because a is what I'm interested in. So a minus 2 will be equal to b. From here, a minus 3 is equal to c. And here, it doesn't really matter. This one doesn't really help us. So these are the two that I'm going to sub back into this one to solve. So let's do that. We've got a squared minus b, which is a minus 2 squared, minus c, which is a minus 3 squared, plus a times b, which is a minus 2. And that is equal to 2011. So we have a very manageable equation now. Let's do the math, algebra here. A squared minus a squared plus 4a minus 4. And I'm just basically expanding this. There's no tricks here. Minus a squared plus 6a minus 9, and then this is a squared minus 2a. And that's all equal to 2011. So let's see here, those two cancel. This a squared cancels with that, so that's very good. 4a, 6a, that's 10a minus 2a, who have 8a. And then on the other side, I got 2011 plus 4 plus 9. And this becomes 8a is equal to 2011 plus 13, so that's 2024. And therefore a is equal to 253. So there you go. Number 21, the answer is E. Distinct planes P1, P2 until Pk intersect the interior of a cube Q. Let S be the union of the faces of Q, and let P equal the union from J equals 1 to K of Pj. The intersection of P and S consists of the union of all segments joining the midpoints of every pair of edges belonging to the same face of Q. What is the difference between the maximum and minimum possible values of K? Let's explain this question first. They want us to take this cube and cut it by slicing it with planes. And when we do that, we have to ensure that all of these diagonals have been sliced through. And that's what they mean, that when you join the midpoints of every pair of edges, so every pair of edges has a midpoint. For example, this is a midpoint, this is a midpoint, this is a midpoint, and that's a midpoint on the top face. And when you join them, you get these lines, as you can see. And when you join them like that, the planes have to cut through every single one. So every single one of these lines that connects midpoints has to be cut. The planes have to slice through all of them. And we have to talk about what is the maximum number of planes we need to have in order for that to be achieved, and what is the minimum number of planes. And then once we have the maximum and minimum, we subtract them, we get the difference. So we have to count how many planes. But how do we do that? Like, it gets confusing very quickly. So let's break it down into simple way of doing it. And we're going to make a little table here. So what I'm going to put in this first column is the number of diagonals that the plane cuts. The number of diagonals cut by plane. And here, the number of such planes. So let's start off with the most obvious, in my opinion, is the ones that actually don't cut through any diagonals. See, these are diagonals, right? This is a diagonal, this is a diagonal, and so on. But there's some that don't cut any, 0 diagonals, and those are these ones right here. The ones that go like that. That is a plane. It will cut the cube in half, right? And that, obviously, there's one of those. But there's another one here that cuts it in half, top to bottom. And then there's another plane that would cut it in half like that. So as you can see, there's 3 of those planes. The first one was here, right? The second one was here. And the third one is here. So 3 such planes. So there you go. And remember, those are planes that have the unique property that they don't go through any of the diagonals. Now let's talk about planes that go through 2 diagonals. And those are planes such as these. This one. Now you say, well, I only see one diagonal because the second one's down here, right? It's not been drawn in. That plane cuts the cube in such a way that it hits 2 diagonals. Here's the first diagonal, and here's the second diagonal. But how many such planes are there? Well, I just drew one. I think there's going to be quite a few of these, actually. I think there's going to be 4 on each side. Like that. And what I really mean by that is 4 that begin on each side. So, for example, you see this one here, it begins here, so you can kind of call this as sort of the beginning point, and then it chops right through. There's another one that will begin here, another one that will begin here, another one that will begin here. So 4 that begin on each side. Now, if you looked at it from the bottom and counted those 4, those are exactly the same. So we don't need to count those. So 4 that begin on the top, but the 4 that begin on the bottom are exactly the same. So those are just 4. And then very similarly, if you do the same thing here, right? Those, if you chop them through in the very same way, they will create another 4. And very similarly on this side here, it will create another 4. So 4 plus 4 plus 4, which is of course equal to 12. So I hope you understood that. I mean, just if you didn't, rewind back and listen to me again, and I'll just recap really quickly. The top one is easiest to explain. There's one slice, right? Very similarly, there's going to be another plane exactly like that there, another plane there, another plane there. That's 4 planes that go top to bottom. But if you count those same planes emanating from the bottom, they're the exact same. So the top and bottom consists of 4. The 2 sides will consist of another 4, and the front face and the back face will consist of another 4. And that's why you have 4 plus 4 plus 4, which is 12. Okay, now we get to the next set of planes that are defined by 3 diagonals, meaning they cut through 3 diagonals. And those are these ones here. This one. That's a plane that cuts through 3 diagonals. It basically chops off a corner there. And those are a little bit easier to understand, I think, because you can do that at all the corners. So there's one, there's another one that you're going to do, there's another one, and there's another one. That's 4. And at the bottom, you'll have the same story. Corner here, corner there, and there's a corner that we can't see. So 4 corners on the top, 4 corners on the bottom. Basically, each one removes one of these vertices. And of course, there's 8 vertices. So there's 8 of those types of planes. So this is 8. And then the last one, the last type of plane, is a plane that cuts off 6 diagonals. That's a little bit harder to visualize. It's like this, like that. That one, as you can see, 1, 2, 3, 4, 5, 6. There's 6 diagonals that plane goes through, and there's going to be one emanating from the top here, another one from here, another one from here, and another one from there. So there's going to be 4 of those types of planes, each one starting from one of those different points that I drew an arrow to. So there's 4 of those guys. So we've got 4 for that one. And there you go. That's the total. So that's what? 3 plus 12, 15 plus 8, 23 plus 4, 27. So 27 is the total. And because 27 is the total, 27 represents the maximum. Now our task is to also figure out the minimum number of planes such that every single one of these diagonals is covered, and also every single line that joins midpoints is also sliced through. That line, every single line has to be cut through by some planes. And the question now is, what is the minimum number of planes that I can use to cover all of these lines that I'm drawing in red? Well, obviously it has to be some of these guys. Those are the maximums, so we have to choose from those 27. Now, which ones though? Well, I think I can do it first and foremost by using these guys. These guys will cut down like this. That was the first one. This is the second one. And this was the third one. Those 3 planes will cut through quite a few of those lines. So I'm going to use those 3. Those are the ones that cut through 0 diagonals. Then, if I use these guys, I will be able to cover every other diagonal. Interestingly, you will see that. That cuts through everything. And then you'll see, like, it's hard to draw it all, because it's 3D and I cannot see 3 of the faces. But once you, I encourage you, if you're practicing, make a little cube for yourself. You can use a Rubik's Cube, or you can just make a paper cube and do that. And you'll see that all of those midpoints, all of those lines that join the midpoints from the edges will be covered if you use these 4 planes that belong to that category of planes. So what is the minimum? Well, the minimum is 7. So the difference between the maximum and minimum is 27 minus 7, which is 20. So the answer to number 22 is C. Let S be the square, one of whose diagonals has endpoint 0.1, 0.7, and negative 0.1, negative 0.7. A point V, which is xy, is chosen uniformly and at random over all pairs of real numbers xy, such that x is between 0 and 2012 and y is between 0 and 2012. Let T at V be the translated copy of S centered at V. What is the probability that the square region determined by T at V contains exactly 2 points with integer coordinates in its interior? Points with integer coordinates are known as lattice points. So I will refer to those points as lattice points throughout the question. So let's, explore this first by drawing a basic square. Now this square is most likely on a slant because of the coordinates like this. It's something like this, right? And they tell me that you've got a diagonal and it has endpoints 0.1, 0.7, and the other one is negative 0.1, negative 0.7. Okay, well, we can easily figure out the diagonal distance. That's not a problem. We can really quickly do that. That's going to be 0.1 minus negative 0.1, so it's going to be plus 0.1, all squared, plus 0.7 and minus negative 0.7, so also plus 0.7 all squared, and then take the square root like this. And then that's going to be 0.2 squared, which is, of course, 0.04, and then this is a 1.4 times 1.4, which is 1.96, and this is all squared. So this is just root 2, interestingly, the diagonal. So if the diagonal is root 2, and the side length is, let's say, x, then we can get that x squared plus x squared is equal to d squared. 2x squared is equal to 2. That means x squared is equal to 1. X is just 1. So this is basically a unit cube, or a unit square, I should say. It's not a cube. Well, I think I can work with this now. If it's unit, then that means this is 1, and so on, right? Okay, so now let's figure this out. And since this is a square, this point right here would be minus 0.7 and 0.1. So what I can do really quickly is sort of draw a triangle like this. Not perfectly drawn to scale, but it's okay. You kind of will hopefully get the gist of it. And this part here is basically the up and down y part, so it's 0.1 to 0.7, so that's 0.6 in terms of its length. And then this part here is going from negative 0.7 to 0.1, so that's going to be 0.8. And this is, of course, a right angle that I drew. So this is going to come in handy, this relationship, hopefully later on in the question. Okay, so now we've exhausted this, we've talked about this. Now let's get to the heart of the question. What they're doing is they're taking this square, right, that we've talked about, and they're moving it somewhere else in the coordinate plane, somewhere way out there. And it's only in the first quadrant, right, because x is going from 0 to 2012 and y is going from 0 to 2012. So we're only in the first quadrant. Somewhere in the first quadrant, they're going to draw some point V, and then they're going to put this square right on top of that V, so that V is the center, like this. And they're then asking you, is inside that square, how many lattice points are there? Okay, that is the essential explanation of the question. Well, we definitely need a diagram for that, so here we go. This is my diagram, so let's explain what's happened here. This is my square that I had talked about previously. I've moved it somewhere, and then these are my lattice points right here. Here's the first one, here's the second one, third one, fourth one. And I want to place the square in such a way so that I can cover two of them, because they want two lattice points. So first let's talk about this. If the square is placed like this, am I succeeding? Have I covered two lattice points? And the answer is no. I've only covered one. But if I move the square over all the way to here, have I now covered two lattice points? And again, the answer is no. Now I've covered a different one, but I still haven't covered two. So I've got to place the square in such a way that I cover two. So that means that the V's got to go somewhere here. The center has to go somewhere here. That's what those shaded regions are. So the V has to go here. And if the V goes there, then I'll just draw it really crudely. The square will be like that, right? And there you go. You got two lattice points. And that is the gist of the question. They want you to find all the places that you can put V, which is the center of the cube, center of the square. I don't know why I keep saying cube. And the shaded regions here are the regions where V can be placed in order for that square to cover two lattice points. And the lattice points are right here. All right. So our job now is to figure out the area of those shaded regions. So how do we do that? Well, we had touched on it very briefly in the previous part, that we had drawn some dimensions, and those dimensions are really going to help us. First, let's draw a line from A1 to A2 like this. And that line is basically a translation. You've moved it over 1 unit. So that distance from A1 to A2 is 1. And now I'd like for you to concentrate on this triangle right here. A1 down to this I, and then down to A2. And we are going to look at those lines and try to figure out the distances. Well, we had previously done something very similar. We had drawn a triangle like that, and we had looked at the coordinate points and deduced that it's a unit square, so this is of course 1, and that this was 0.6 and this was 0.8. So we can use the same distances for this triangle right here. It's basically going to be a similar triangle, since this is a right angle, this is a right angle, and the other two angles will also be the same, right? Because this is a right angle, and whatever angle this is going to be 90 minus x, and therefore this is x, and then therefore this is 90 minus x, those angles. So those are indeed similar triangles. So since they are similar triangles, this is going to be 0.6, this distance from here to here, and this distance from here to here will be 0.8. And since this right here, from here to here, is the edge of a square, our square, and our square has an edge of 1, from here to here has to be 0.4. And very similarly, from here to here is an edge of the square. If this is 0.8, then this guy is 0.2. Squeeze that in there, 0.2. So now I've got a rectangle with dimension 0.2 times 0.4. So that area of that rectangle is 0.2 times 0.4. But I only want half of it because, remember, the shaded region is only half of that. So just divide by 2. So 0.2 times 0.4 divided by 2 is 0.04. But I've got 4 of these regions, right? I just calculated the area of one of them. So if I want the area of all 4 regions, multiply that by 4. And when I do that, I get 0.16. And that is the probability. It's the probability that if V is going to be placed in those shaded regions, that you will get the square covering exactly 2 lattice points. And therefore, number 23, the answer is C. Let AK from k equals 1 to 2001 be the sequence of real numbers defined as written here. And more generally, with this definition right here. Rearranging the numbers in the sequence of AK in decreasing order produces a new sequence with BK. What is the sum of all the integers k, where k is between 1 and 2001, such that AK equals BK? Our task in this question is first to get a pattern as to how A1, A2, A3, and A4 behave in terms of how they relate to each other with regard to being greater or less than each other. And then once we have that, then we can reverse them and get BK, and then we see which ones match. Which ones match in terms of AK equal to BK. So the first thing I want to explain is that these numbers are all very similar. They're all approximately 0.2. So if you have 0.2 to the power something, right? How does that behave in terms of a graph? Well, we can draw a quick sketch. And it will behave as follows. And some of you, of course, already know this. When x is 0, this was, of course, going to be 1. When x is, say, 2, this number, 0.2 to the power of 2, will be 0.04. It actually gets smaller. So it behaves something like this. Right? And the only reason it behaves like that is because this number is less than 1. So that is a very important thing. As the x values get bigger, the y value gets smaller, but only because that's a small number less than 1 greater than 0. So now that we have this graph, let's compare A1, A2, A3, and A4 and get some sort of an order. So let's start off comparing A1 with A2. A1 is 0.201, A2 is 0.2011 to the power of A1. Now, if you just look at the bases, the second base is slightly bigger. But I haven't compared the exponents. That exponent is just 1, and this is A1. But A1 is 0.2, so obviously A1 is less than 1. So that means we are going this way. If, for example, if 1 is here, 0.2 is here. So that means it's going to be higher on the graph. When the exponents are less, the number becomes bigger. So that means that this is indeed greater. So my first comparison leads me to believe that A2 is greater than A1. All right? So let's compare A2 and A3. A2 is 0.2011 to the power of A1. A3 is 0.20101 to the power of A2. Let's look at the bases. This number is greater than that number, so I'm tempted to put a greater than sign, but I still have to look at the bases to be sure. A1 and A2. Well, I just proved that A2 is greater than A1 up here. So since A2 is greater than A1, that means that if you're going this way, the numbers are getting smaller. So if I have a larger exponent, the number will be smaller. So that means, indeed, this holds true. So that means that A2 is greater than A3. That is my second finding. Now let's compare A1 to A3. A1 is 0.201 and A3 is 0.20101 to the power of A2. Well, if you compare the bases, this base, the second base is bigger, so I'm tempted to put a greater than. But then what about A2 and 1? Well, A2 is right here, right? It's 0.2 to the power of 0.2. So it's approximately 0.4. And 0.4 is obviously less than 1. So you're getting on this graph here, if you compare A2, which is about 0.04 to 1, 0.04 is obviously less than. So you're going this way. And therefore the number will be bigger. So this is indeed going to hold true. So that means that A3 is indeed greater than A1. All right, so we've got 3 comparisons. We're going to make 2 more comparisons, and then we can create a sort of a general understanding. Next, I'm going to compare A3 and A4. A3 is 0.20101 to the power of A2, and A4 is 0.201011 to the power of A3. So by now you're a pro at this. Let's compare the bases. 20101 to 201011. This base is obviously slightly bigger, so I'll put in the greater than sign for now. But let's compare the exponents, A3 and A2. Well, we had just earlier concluded that A3 was less than A2. So we're going this way again. And if you're going that way again, then the numbers are getting larger. So indeed, that holds true. So that means that this, which is A4, is greater than this, which is A3. So A4 is greater than A3. And then one final comparison, A2 and A4. A2 is 0.2011 to the power of A1, and A4 is 0.201011 to the power of A3. Well, let's look at the bases. This base is bigger, so I'll put a greater than. But let's also compare the exponents, A1 and A3. Well, A1, we had earlier concluded, was less than A3. So we're going this way. So if A1 is less than, that means it creates a number that's going to be greater than. So indeed, this holds true. Therefore, A4 is indeed greater than A2 is greater than A4. Now let's combine these results. These 5 results that I got, 1, 2, 3, 4, 5, these 5 inequalities. Let's combine them all, rank them from smallest to largest. If I do, A1 is the smallest, and then that is, and the next one in line would be A3, and then the next one would be A4, and then the next one would be A2. And if you see, all of these inequalities will hold true if this is the order. So now, without having to go on and do A5, A6, A7, we have to conclude, make some conclusion. And that is that whenever the number here for any AK is odd, it will create increasing values. So as you can see, A1, A3, like that. And when K is even, it will create smaller values. And also, the even ones will always be greater than the odd ones. So now that we have done that, we can now move to the final part of the question. That now they are creating a new sequence with B's. And what they're saying is first write out all your A's, and if we did, it would be A1, A3, A4, A5, because first all the odds, A7, and then ... all the way until the very end. And on the other end of the spectrum, eventually it'll be A8, A6, A4, and then A2. And this is, of course, in increasing order. Now, the B's, these are the A's, right? These are all the AKs. Now, the B's, the way they're doing those is that they were just reverse the order. So they take these guys and they just reverse them. So they start on this end and they write B1, B2, B3, B4 like this, all the way down to, we're going up to 2011, right? So this would be B2011, this would be B2010, B2009, and B2008, like that, and so on. All right, so now what they're saying is, when does AK equal BK? When do these match up? Well, to do that, we have to sort of look at a general pattern as to how BK and AK behave. BK behaves in the way that each term looks like it's 2011 minus K. So, for example, when K is 1, this would be 2010. And then AK behaves as follows. Each A, it looks like it's just odd numbers initially. So it's behaving as 1 plus 2K. So for example, when K is 1, it's going to be 3. So as you can see, when K is 1, that's this scenario right here. AK becomes A3 and BK becomes 2010. When K is 2, it becomes this scenario. When K is 2, it becomes, if you plug 2 into here, that becomes a 5, and then this just becomes 2009. They're saying for what value of K is AK equal to BK? Well, that's the same as saying when is 2011 minus K equivalent to 1 plus 2K? And if you do the math here, it is going to be 2010 is equal to 3K, and therefore K is 670. So when K is 670, so somewhere in here, somewhere, we're not sure exactly where, but 670, what is going to be my value for A and B? Well, when K is 270, we have 2011 minus 670, and that is equal to 1341. So that makes it A1341. And then that's B. And then now let's figure out A. A would be 1 plus 2 times 670, and that's going to be 1341. So there we go. That's 1341 right there. So 1341 is the only value of K. So the sum of all values of K is just 1341, interestingly. So the answer to this question is C. Let f of x be the absolute value of 2x bracket minus 1, where x bracket denotes the fractional part of x. The number n is the smallest positive integer such that the equation n times f at x is equal to x has at least 2012 real solutions x. What is n? Note, the fractional part of x is a real number, y is equal to x bracket, such that y is greater than or equal to 0, less than 1, and x minus y is an integer. Well, this question requires some graphs. And this is the first one. This is the graph of f at x. And that is the absolute value of 2 times x in a bracket, like that, minus 1, where x is the fractional part. X bracket is the fractional part of x. So as you can see, you got 1 up here, and you've got 1 down here, and so on, right? So it's a zigzag pattern. Now what we have to do is draw 2 more graphs. And the next graph we have to draw is the graph of f at x times x, that one. And that one, I will walk you through that one. Let's draw this pattern here, and off we go. So again, I'm going to draw this a little bit bigger in terms of like the values, because I've got to squeeze it all in. So let's see here. It won't be perfectly drawn to scale, but hopefully you'll get the idea. So if you were to just look at this graph right here, and then all you're doing is multiplying by x every time, then you get the following pattern. And let me just label this in now. 1, 2, 3, and this is 1, 2, and 3. And that's the zigzag pattern you get this time. As you can see, it's a little bit different, but it still is a up and down type of scenario. Now you think, okay, well that doesn't seem so bad, but unfortunately we have to now draw this one. Remember, f at x now has to be put inside that. So it's going to be this monster right here. And if we go back to the original definition, this is actually the absolute value of this time the bracket has x times f at x inside, and then minus 1 absolute value. So now we got to draw this. So this one is a little bit trickier, but there's some good news here that it never gets bigger than 1. So that's why the axis here on y is only 1. So in the initial part of the graph, it's behaving in a way that's kind of strange up there. But then eventually it drops down to the 0 and then goes right back up to 1. So that's the first part. And then from 1 to 2, it starts developing a pattern that is very helpful to us. It drops down like this and goes back up to 1. But then in the second half, from here to here, it actually drops down twice. So it'll come down once, come back up, and then come back down again, and then come back up. And then from 2 to 2.5, it will again come back down and go back up twice. So once, and then twice, and then once, and then twice. But then from 2.5 to 3, it'll come back down and up 3 times. So once, twice, once, that twice, and then a third time here. So like that. And then that's the pattern. Now, this has to equal, if you remember, x over n. So x over n is obviously some straight line, and it has to equal. So it's going to go through somewhere like that. We're not entirely sure, but something like that. And the intersection points are basically the solutions to this equation. So we have to start counting intersection points, okay? From 0 to 1, it looks like 1, 2 intersection points. So let's put that there. 2 intersection points. And then from 1 to 2, we have 1, 2, 3, 4, 5, 6 intersection points. So I'll put 6 there. And then from 2 to 3, I've got 1, 2, 3, 4, 5, 6, 7, 8, 9, 10 intersection points. So I'll put that there, 10. So as you can see, each time it's going up by 4, like that. So if I were to do from 3 to 4, it would be 14 intersection points, and so on. So that means this behaves as follows. The intersection points will be 2 plus 6 plus 10 plus 14 and so on, right? Dot, dot, dot. Now, if you were to factor out a 2, you will see this is 1 plus 3 plus 5 plus 7 plus dot, dot, dot. And that's obviously the sum of the first n. If it goes all the way up until n, it's the first n odd numbers. And the sum of the first n odd numbers is always equal to just n squared. So this is just 2n squared. And our question says that we want more than 2012 solutions. So that means this 2n squared has to be greater than or equal to 2012. So that means n squared has got to be greater than or equal to 1006. And the first time that you get an integer solution for this is when n is equal to 32. So the answer to this question is 32, which is choice C.